Okay, let's dive into this. Welcome back to The Explainer. Today, we're taking a look at a topic that, honestly, usually gets treated like dry chemistry on a chalkboard. But we're going to reframe it. We're looking at a full-on molecular drama. It's this epic story of theft, of lonely molecules, and ultimately of perfect matchmaking. So, let's unlock the secrets of the Wurtz reaction.
Section 1. The chemical copy and paste.
So if you're studying organic chemistry right now, trying to build larger molecules can feel kind of tedious, right? It's a complicated task. But what if you had an ultimate shortcut? I want you to imagine this reaction as basically a chemical copy and paste tool. Like, are you tired of tiny carbon chains? Do you want to double your molecule size with just one simple reaction? Well, look no further than the Wurtz reaction. In the organic chemistry world, this is pretty much a magic wand. You take a small alkyl halide molecule and it literally doubles its carbon chain. It's quick, it's efficient, and it's an absolutely perfect shortcut for building bigger structures.
And this brilliantly illustrates exactly what we're talking about here. Think about the absolute simplest thing, snapping two single Lego bricks together to double their size. You know, we've all done it, it's incredibly satisfying. Well, this is the exact chemical equivalent of that. You're taking an alkyl halide, taking a second identical one, and just snapping them together. Boom! Now you have doubled the carbon chain into a larger, perfectly symmetrical alkane. That right there is the whole essence of the Wurtz reaction. Just two identical building blocks clicking smoothly into place.
Section 2. Ingredients and explosive hazards.
Okay, but before we go snapping our chemical Legos together in the lab, we really need to talk about what it actually takes to make this happen safely. Because, while the theory is wonderfully simple, the laboratory reality requires serious respect. We've got a surprisingly simple 3-ingredient recipe. We need our alkyl halide, that's the building block. We need sodium metal, which is what actually makes the reaction happen. And we need a solvent called dry ether. But take a look at the hazards here. Sodium isn't just your average metal. It is fiercely reactive. Actually, it's usually stored completely submerged in oil, literally just to stop it from reacting with the invisible moisture in the air.
Which brings up a massive, high-stakes question. Why must the ether solvent be strictly dry? In chemistry, we use the word anhydrous, which just means bone dry. And the reason for this is, well, pure survival. If that highly reactive sodium metal touches even a microscopic drop of water, it triggers a massive, violent explosion. Just an absolute disaster. So the dry ether acts as this perfectly moisture-free, protective, safe zone. It lets our reaction actually take place without blowing out the lab windows.
Section 3. The greedy sodium thief. All right, now that our explosive safe zone is set up, let's get into the mechanism. And I don't want you to think of this as a boring equation. Think of it as a high-stakes heist. Here's how it goes down. Step 1, our greedy thief, the sodium atom, swoops into the alkyl halide molecule and violently steals the halogen atom right off the carbon chain. Just takes it. Step 2, because that halogen was stolen, the chemical bond shatters. That leaves behind a solitary alkyl molecule. It is completely alone. But here comes the beautiful part. Step 3. Because we have millions of these molecules swirling around in our flask, another greedy sodium has just created another lonely alkyl group right next to it. These two lonely molecules find each other in the solvent, and in this desperate, brilliant matchmaking event, they shake hands and bond instantly.
Now, in formal chemistry terms, that lonely molecule is officially called a free radical. A free radical is simply a highly reactive atom or molecule with an unpaired electron. But in human terms, it's just deeply lonely. That unpaired electron makes the radical desperately seek out a bonding partner so it can feel stable and complete again. And that sheer desperation is exactly what drives the two halves of our molecule to finally click together like those Lego bricks.
Section 4. The symmetry puzzle.
So the crucial point is, this reaction isn't just some magical free-for-all where anything goes. It has really strict rules. First, symmetrical halves act like identical puzzle pieces locking perfectly together. If you start with two identical alkyl halides, they form a perfect, clean, symmetrical alkane. Easy. But what if you try to mix two completely different types of halides together? Imagine a chaotic, super busy party. You've got all sorts of different lonely molecules just bumping into each other wildly. Instead of a perfect match, you get mismatched reactants locking together at random. You basically create this messy, inseparable nightmare mixture that's completely useless in the lab. That's why the golden rule of the Wurtz reaction is that it really only works well for creating symmetrical alkanes with an even number of carbons. Basically, don't throw a chaotic party. Keep it simple and keep it symmetrical.
Section 5. A molecular matchmaking success.
After all that danger with the sodium and following all those strict rules to avoid those chaotic molecular parties, let's bring it all together. The absolute star of this whole successful chemical story is the number 2. Literally everything in this perfectly symmetrical reaction revolves around pairs. To make this perfect match work, you need exactly 2 molecules of your starting material, let's say methyl bromide, and you need exactly 2 atoms of our greedy thief, sodium. Without this perfect pair of 2s, the entire copy and paste process just doesn't happen.
Let's actually see that number 2 in action here. We start with 2 molecules of CH3Br, that is our methyl bromide. We add 2 atoms of Na, our highly reactive sodium. In our perfectly safe, bone-dry ether environment, the sodium atoms steal the bromines. This leaves 2 incredibly lonely methyl radicals. They reach out, shake hands, and triumphantly transform into C2H6. That's a beautifully perfect, completely symmetrical molecule of ethane. Plus, we get 2 molecules of sodium bromide as a byproduct. From methyl bromide straight to ethane, beautifully snapped together. Copy and paste.
Which leads us to a really fascinating thought to leave you with today. If sodium is our greedy thief here, violently triggering this incredible molecular matchmaking,